I love movie trailers. They're like the best 2 minutes of a movie put in a little cut sequence for me to watch. And that's really what this nugget is all about. It's the movie trailer for this series, Core Protocols of a Service Provider. And I'm really excited to get into it because I just got back from meeting with one of the largest service providers in the state of Arizona. And I actually sat down with their system engineers team, it just literally as an interview for this series, saying, okay, tell me what you guys deal with day to day. Tell me the top troubleshooting things. Tell me what key topics of MPLS, et cetera, et cetera. So actually, this slide came from the question, if you were to hire somebody new in your group, what are the key things that you would want them to know? Here they are. IP connectivity, internal routing protocols, multi-protocol BGP, and multi-protocol label switching. So this being the trailer, we're going to do a quick overview of all these technologies and then unpack them in the rest of the series. Here are your do I know this already questions. So if you know the answers to these, move right along to the next nugget in the series. Well, let's start off with IP connectivity and internal routing. When you get into a service provider environment, there are really two distinct layers of routing that happen. The first one most everybody knows about. It's the customer routing, usually using public IP addresses. This is what allows the customers to get online, accessing whatever resources they want to on the internet. But the other layer of routing is the one that not many people know about. It's the service provider internal routing. This usually happens using private IP addresses. One little side note, this is how things normally are done, to where we have the customers getting public IPs and the carrier getting private IPs, but there's all kinds of different ways and designs you can use. I'll give you one example, NAT 444. Right? Normal NAT is actually technically called NAT 44 because you're translating from one private IPv4 address to one public IPv4 address. Well, NAT 444 is where the service provider actually does NAT as well. Here's the idea. With NAT 444, the customer has their router right here, and the service provider assigns that a private IP address. And then behind that router, the customer themselves have their own private IP address, right? So they actually do NAT from their private IP to another private IP, and then the service provider, when it actually does get it out on the internet, does yet another NAT, another layer of NAT, to help conserve public IP addresses. It's one of the advantages of NAT 444 is you can conserve public IP addresses even more by NATing it a second time, but okay, Jeremy's opinion, enter now. Just a bad idea. Number one, it really breaks end-to-end connectivity, even more so to where these guys have a lot of difficulty hosting different, essentially they can't host services, can't run services from their house. It is good just if you want to deliver internet surfing. However, for countries and carriers that are really constrained on the number of public IPv4 addresses that they have, this is something that we need to, they may need to rely on. That's where NAT 444 comes in. So side note aside, let me get back to the way service providers normally use private IPs. It's really this piece that makes people represent a carrier with a cloud symbol. It's because there's a whole lot of complexity hidden behind that vapor, right? This is the internal network of the service provider that there could be, 50, 100 different devices that you're going through that you never see that provide that connectivity. I mean, let's just give an example. This guy, at this house goes to google.com, right? Chances are very slim that Google actually sits right here in the internet service provider that this guy is using, right? So this represents a DSL connection, by the way. He comes into the aggregation point, the DSLAM, hits the broadband remote access server, and this device, by the way, is what gives him a public IP address. This is actually all part of SPN-GN 1, the previous series, but essentially hosts his DSL connection, right? He comes into here, and this is where the service provider does all the correct routing to get him where he needs to go. Now, chances are pretty good that this internet carrier is actually linked to another carrier. Let's just say this is Cox Communications. This is connected to Level 3, and Level 3 is connected up here to CenturyLink, and CenturyLink is, you see where I'm going with this. Eventually, you're going to get to the autonomous system, keyword there, autonomous system of Google.com, and Google is sitting there waiting to give you their web page from some individual server, right? And that travels all the way back through. Now, from this guy's perspective, it looks like he's just like, okay, I'm kind of hopping around on these major internet points, but truth be told, he's going through a lot of internal routing in the middle. So, this is typically the private IP side. And one might argue, one might say, well, Can't it be public IP addresses that we use inside of the carrier? Well, it could. But a few arguments against that and why most people don't do it that way is number one, let me start off with the weak reasons. Number one, think wasting. You don't want to waste public IP addresses on devices that really aren't seen by the public. They're providing the internal routing of the carrier, the stuff that they use to get customer A to the exit point in their network, and that they don't really want that seen by the internet, right? So that would go to a second point, security. And I say these are weak reasons because you could say, well, private IP addresses keep them from being visible from the rest of the world, and the argument is easy to say, well, if you configure your firewall right at the edge, then they shouldn't be visible anyway, public or private IP address. So let me get into the major reason for that. Customer routing versus internal routing really depends on the kind of routing protocol that you're using. Public IP addresses in a carrier are typically routed using BGP, the Border Gateway Protocol, essentially the protocol that ties the entire internet together and allows all these different carriers. I mean, come on, it's amazingly complex environment when you look at the internet as a whole, but if you take a giant step back, it's really simple. All these different internet carriers have their own addresses, their own IP blocks of public IP addresses, and all they do is advertise them to each other, and so everybody knows about everybody. There's just so much connectivity inside the internet, it just feels complex because it is, but the truth be told, it's really just, hey, we've got a bunch of addresses and we want them to be reachable. Welcome to the internet, right? Seems like a commercial or something waiting to be written. So BGP is the one that's designed to handle a routing table that size. Now, I think about BGP, I mean, think about Star Wars, right? Those big old, I don't even know what they're called. I'm trying to think. Let me draw them. They're like these big robots that they look like a truck with stilts, right? You know what I'm talking about on the planet, and they've got these like big robotic legs and a big laser beam right here. It's like choo choo choo, shooting all the little Star Wars guys. Well, the big thing about these guys, if you've seen Star Wars, and up here is the Star Troopers and whatnot. If you've seen Star Wars, these things are like, I mean, the whole ground shakes as they move. They're these big behemoth things, and that's their Achilles heel. Is essentially they're really slow. So the little Jedi Knights on their little I don't know what they're called, air scooters, to where you've got the Jedi sitting on their little air scooter thing, flies around like at lightning speed and wraps ropes around their legs and these things. Oh, that's how I think about BGP. Is it's this big, slow moving. You see the big point here. Big, slow moving protocol by design. You can't have a routing table the size of the internet and be ninja fast. If a network in Taiwan goes down, America doesn't immediately know about. Right? Because it's slow moving getting there in propagating those advertisements, because there are literally thousands of outages that happened in the 10 seconds that I used to speak the statement about those outages. It's always changing all the time out on the internet, and that's what BGP is designed for. So you want to use BGP as an internet service provider to advertise your routes to the rest of the world, but you don't want to use that for your internal routing. I mean, think about modern day carriers. What do they deal with? They deal with voice over IP. They deal with data services that are oftentimes real time. A lot of them, for instance, I just was speaking with Cox Communications the other day, and they deal a lot with IPTV. Essentially television running over an IP channel. Matter of fact, really interesting fact, I didn't know this. They said the number one traffic that they see, they said hands down on the internet, is streaming video. That is constantly saturating the pipes of internet carriers everywhere, because television, I mean, think about Netflix, think about Amazon Prime streaming video, all these different TV online carriers is now, that's where people go. It's a video on demand. And that the reason I say this is all real time. I don't want to dive off into a traffic analysis, because I really want to point out that internally, if a router goes down, let's use green. This router goes green. That's a good down color, right? This router goes down and it flips over. You don't want that to take the time that BGP would normally take. I mean, BGP is like, again, slow conversion, slow to communicate. You want one of these little Jedi Knight protocols like OSPF or ISIS that allows these guys to figure out that this guy is down and flip over in such amazing time that voice over IP doesn't even miss a beat. You're having a phone call with grandma and you don't know that a major failure just happened happen inside of your ISP and it flipped over to a backup router because the ISP designed their internal network correctly with these Jedi Knight routing protocols. So we now move from Jedi Knights into the last two core protocols of a service router. In this overview, MPLS, that's multi-protocol label switching, and MBGP, that's multi-protocol BGP. Are you sensing a theme? Multi-protocol, right? In both of these concepts. So I'm taking this picture from the previous slide and now blowing it up a little bit. So we've got this cloud, which now is seen. We're seeing the internal mechanics of this cloud. We've got the customer, which is now represented as this, kind of encompassing this whole group. And then we've got some businesses that are also connecting into that cloud. And I want to make sure, first off, I differentiate it. This is a service provider. Right? A lot of times we use service provider and internet service provider interchangeably, but in reality they're actually a little different. An internet service provider is one who focuses on delivering internet access to its customers. Yeah? And then a service provider is one who delivers connectivity to its customers. So they could very well, almost all service providers, I will say, are also internet service provider, but here's the difference. These guys are coming through here to surf the web, so they see this service provider as an ISP. Right? That's what they'll call it. Whereas these guys may be coming through the service provider to connect to the web, so they would call it an ISP too, but also to connect to each other, so they would just call it a service provider. Right? They are using the infrastructure of the service provider to bridge their two offices together. Okay, so with that piece laid, let's talk about MPLS. What is multi-protocol label switching? Well, number one, it is a way of keeping things at layer 2. Right? So talking about the OSI model, let's just talk about how traditional routing works. So let's just say this is a just for ease of this example, let's just say this is an Ethernet everywhere service provider, right? So we've got this customer right here that has a computer inside of their house. They say, I want to ping, let's just say ping 4.2.2.2, a DNS server, right? This router right here realizes that that address, 4.2.2.2, is not in the house, right? Because it looks and it goes, well, this computer, if it's like every home in America, is 192.168.1.50. And 4, if I look at that subnet mask, 4 is a completely different network than 192. So I'm going to send that to what? Default gateway, right? Okay, now here's the key. Catch this. Default gateway looks at its what? Routing table, RT, routing table, and says, okay, I am a dumb Netgear router. Who would ever buy one of those things? I'm going to use 0.0. I'm going to use a default. I should not slam Netgear. Strike that from the conversation. Netgear is a quality product. So this high-end device looks at its routing table and realizes, I don't know anything except send this to my ISP. Now, how does it know who his ISP is? Well, it looks at its public interface, looks at its routing table, and says, well, on this side, I'm 1.1.1.1, let's just say. And the gateway over here is 1.1.1.2. So it looks at its routing table, says, okay, well, I'm going to rip off the MAC address, the source MAC address of forgive my penmanship. Let me change colors here. The source MAC address of this guy and the destination MAC address of me, and replace it with the source MAC address here and the destination MAC address here. Shoop, packet is received, right? Again, Ethernet everywhere. What are we going to do? He's now looking at his routing table saying, okay, do I know how to get to 4.2.2? Oh, sure. It says go here. So I will then rip off this source and destination and replace it with the source and destination MAC address right here. Sends it down here. This guy, last time I'm going to do this, right? This guy looks at its routing table, saying, okay, you're going to the destination IP address 4.2.2. Let me look in my routing table. I really am emphasizing that here. Okay, where am I going? I'm going here. Source, destination, rip off this, replace it with this, and now the packet goes to the next step. It just keeps doing that the whole way until it reaches 4.2.2.2. I mean, just pause for a moment and say, wow, it's amazing that that can happen in a matter of milliseconds, right? And make its way back in the network. So insane how fast technology is, but let's make it faster. MPLS, number one, is a layer 2 technology. What happens? Let me erase this out. When you enable MPLS on these devices, now let me emphasize, MPLS is typically a service provider technology. It doesn't have to be, but almost solely in reality a service provider technology. When you enable MPLS on here, these routers generate a label for every route in their routing table. Now, what's a label? It's really just a number, just a little tag, if you will, that is assigned to those. So let's just say in this guy's routing table, remember this guy pinged 4.2.2.2, right? So in here, this guy's routing table, he's got a route, let's just say to 4.0.0.0/8. So he's got a route in there. He'll assign that label, let's just give it 101, right? This guy in his routing table has the label for 4000 being 201. Right? And then this guy, let's just stop right here. This guy will assign 4000 301. Right? Now these carrier routers, I should say, speak together. They form relationships and start distributing labels to each other using LDP, the Label Distribution Protocol. All that means is, let's just say router 1 and router 2 start having a friendly conversation. Router 2 is like, hey, router 1, did you know that I've assigned my 4000 network the label 201? Hey, router 1, oh, that's fantastic. That's great. Matter of fact, I've assigned that network 101. So they kind of exchange their little labels in here. So here's what happens. When this guy sends the packet to 4.2.2.2, the very first router in the MPLS network immediately puts in the header, so here's the destination IP is 4.2.2.2. He puts in the header a label. He looks at his routing table and says, okay, well, it's going to this guy next, and I know in his routing table will be the label 201. Right, so it puts 201 as the destination label, if you will, the destination MPLS tag in the header, and sends it its way. Now this guy has communicated with router 3 over here, and he knows that router 3 has given 4000 the label 301. And he makes the correlations in his table to say, okay, well, if I've got 201 on my side, 301 is the label that I'm going to use whenever I communicate to label 3. So he pops the label off, he takes off 201 and puts on 301 in that case, and then sends it on its way. So what did he do? He just took that packet without ever looking at the IP address it's actually going to, without ever looking at the routing table, which has been the way that we've done routing since the inception of the router. It just says, I'm just going to look at what label I have on there and figure out where it's going and replace the label. So I keep it all the way, let me put that back on there, I keep that down at layer 2, thus increasing the speed of the routing. Insert disclaimer. Disclaimer is that this would be a very valid statement a decade ago, when routing was a pretty slow process. But since then, I mean, you hear about technologies like Ceph, Cisco Express Forwarding, right? That's just one of many routing caching technologies that have been invented to speed up layer 3 routing in Cisco and in every other vendor that's out there. So I've heard MPLS as Ceph, Cisco Express Forwarding, for the masses. Essentially, instead of having this proprietary Cisco Express Forwarding and then, Juniper, with whatever they've got, Jeff will say, everybody's got their own little caching technologies that speed up layer 3 routing. So nowadays, if you were to come in and say, well, we use MPLS because it really makes everything lightning speed through the carrier network, well, that would be accurate. I wouldn't say that would be the main thing that people think about when they think about MPLS. The big thing that it does, and it goes right along with this, is it allows the carriers to route without looking at the layer 3 information. Why is that relevant? Because it leads into these two technologies, L2 VPN and L3 VPN. Big things that you want to know right now. L2 VPN and L3 VPN is what MPLS makes possible. L2 VPN, I know some of you might be thinking VPN. I've heard that before, right? Virtual private network. What most people think about with a virtual private network is I've got my, well, that shouldn't be a cloud. Let's just say I've got my company right here. I'm sitting on a laptop on the road or in a hotel or something like that. I open the Cisco VPN client and I run a IPsec based or encrypted connection to the company, and now my laptop is essentially like it's sitting at a desk in the office because I can access all the same resources. That's what most people think of when they think about virtual private network, which is absolutely correct. That's one application of a virtual private network, not to be confused with MPLS's L2 VPN and L3 VPNs. L2 VPN allows a business to use the carrier as if it were their own. I don't want to get too deep into it at this point, but here's the overview. Let's just say that I've got this office up here, CBT Nuggets in Oregon. This office up here is CBT Nuggets in Arizona. With L2 VPN, essentially the service provider can bridge think of it like a tunnel, although it's not truly like an encrypted VPN tunnel, but it's a virtual tunnel created through the carrier network to where literally this guy could take this cable, if it's an Ethernet termination, plug it into a switch, and take this cable and plug it into a switch here, and bridge the two networks through the carrier. Like this is one big old Ethernet cable that goes from Oregon down to Arizona. Right? And as we bring up CBT Nuggets Hawaii, which is going to be my personal office, we bridge that right into the tunnel to where we connect it to the switch, and this bridges the network into this office to where essentially the service provider cloud looks like one big flat layer 2 switch, as if this I wish I could visualize this. All these offices were plugged into a 3-port switch. Right? This guy, and this guy, all plugged into that 3-port switch, and they have full connectivity. Now, how is that possible? I mean, think about it from a routing perspective. Let's just say CBT Nuggets in Oregon is 10.1.0.0/16. CBT Nuggets Arizona is 10.2. Hawaii is 10.3.00/16, right? We've got these different subnets. But then the service provider also brings up another customer. Let's just say Tonka Trucks. Adds a office up here, and they decide I want to use 10.1.0.0 for my network and connect to Tonka Trucks is at Tonka, Arizona, and I want to connect to Tonka Truck, New Mexico. So I'll put NM right here, which happens to be 10.2.0.0/16, right? Whoa, we've got a problem because this network, if the service provider is kind of allowing this customer to use their network and CBT Nuggets to use their network, we've got a conflict. 10.2 and 10.2 here is now a duplicate address, but coming back to what is the goal of MPLS, the service provider can hide, never even see the layer 3 information that the customer is using. By putting that label on the front of the packet, they can forward it right through their network and only look at the labels. So the routers use the labels to make sure Tonka, Arizona reaches Tonka, New Mexico, but they never have to look at that layer 3 information. Now, if that's what that is, what is a layer 3 VPN? A layer 3 VPN is where the service provider, man, this slide is getting messy, the service provider can participate in the routing of the customer. So check this out. The customer, I just said a layer 2 VPN is where they're kind of using, like this cloud looks like a big switch to them. And that's really kind of how it works out from their perspective. They can manage they can send VLANs through that service provider network that terminate over here. I mean, it really just bends the rules of everything that we thought a service provider network would be. So a layer 3 VPN allows the service provider to create a virtual router. Matter of fact, you'll start seeing terms like this, virtual router forwarding instances, to where they create a virtual router. I mean, very similar to the way VMware creates virtual servers on a device, a router that essentially participates in this customer's network. Participates so much so that, for instance, the service provider and the customer can form an OSPF relationship. Or even EIGRP. I've seen this done a couple times where the service provider is running a Cisco router, the customer is running a Cisco router, and literally it bridges, or I should say forms, a routing neighbor relationship with this customer and exchanges routes from this customer to the carrier, who then forms virtual relationships with VRF instances over here, and forms maybe an OSPF neighbor with this office, the Arizona office of CBT Nuggets, and exchanges routes right here. Essentially, the service router begins participating with you, customer. Well, it's weird. It's weird teaching a service provider series because I'm so used to being on this side of the table that I never know which identity I am, right? So we, the service provider, are talking to customers using routing protocols and allowing their routes to go through our system. Hello, creepy. Right? Because now we have relationships with customers that we don't trust, but using MPLS, we can hide all of their information behind a label, allowing them a lot of flexibility in the way that they do routing, allowing them flexibility with quality of service. I mean, there's a lot of advantages to L3 VPN that we'll talk about a little bit later, but that is now possible because we're using MPLS. Now, you're like, good grief, this is getting a lot of stuff. So let me just quickly talk about MBGP. What is MBGP? This is the routing protocol. It's essentially an extended version of BGP, essentially the routing table of the internet that allows us to tag routes, separate routes, different instances of routes. I mean, similar to the same way that MPLS allows you to use labels to hide information, multi-protocol BGP uses, if this doesn't make sense at this point, totally get it, but it uses things like extended community tags to do the same kind of things that MPLS does, separate and hide customer information, but yet route it through the service provider network. Man, it's hard for me to do these movie trailer overview style things. I just want to dive into the abyss of information that's available. But let's pull back. This is the core protocols of a service provider, and I would say your MVP topics that we will be unpacking through the series. IP connectivity, internal routing, those ninja fast protocols like OSPF and ISIS that are used inside of the carriers to do the routing themselves, and then external routing using like BGP, and then multi-protocol BGP and MPLS integrated together, allowing us to truly integrate with customer networks, allow customer networks to flow through us as the service provider, and yet hide their information behind the beauty of a label. Awesome. I hope this has been informative for you, and I'd like to thank you for viewing.